We're about to introduce the genetic algorithm, go into the details of it. We had just discussed the primary usage of a genetic algorithm as an optimization algorithm. So here's a sample of an optimization algorithm or an optimization problem. The key notation is X is some sort of space of instances, and our goal is to evaluate some function so as to find the minimum or the maximum. So for instance, we map X to R, and so that would define some surface or landscape for us. Machine learning and science are full of optimization problems. Here's some optimization problems you may have seen already or may be familiar with. I'm sure you could come up with a few more problems that you're familiar with. Many optimization techniques, we mentioned a few: enumeration, random search, dynamic programming, gradient descent, hill climbing, simulated annealing. We discussed what are some things that cause difficulties in optimization, or what makes a problem easy. Linear regression, in some sense, it's easy. It's defined everywhere on kind of the whole space of Rn, and we have a smooth function where we can find lots of information about. One can take a gradient. One knows which way is the direction of steepest ascent, which way is the direction of steepest ascent. Something which thrown into an optimization problem slightly makes it a bit harder is constraints of some form. These are simple linear constraints, but actually makes the problem a lot easier, because now harder in the sense that, for instance, if you were using a gradient to move around on, you have to worry about, you can't just move in the direction of steepest descent, because you might go through a constraint. These linear constraints define some polygon in which the function which we're trying to optimize lives. So constraints make a problem harder. We still have a lot of smoothness, but suddenly we've added in a discrete element. And then when we start to define the problem over a discrete space, suddenly things are far worse. We have no clean definition of a gradient. We can't hope, our directional information is somehow weaker. There's, here more than a gradient, you have Hessian, you can take second order derivatives, you can get all sorts of information about the surface locally, or you can do good estimates. And likewise, we see a progression in time. Linear regression is maybe cubic in the worst case, but often much faster. Linear programming, it's a high order polynomial in the worst case, and this is an example of imposes a decision problem, the NP-complete problem. So we have this kind of hierarchy of things which makes the problem difficult. Genetic algorithms have been most successful with discrete optimization problems. So let's just jump into how a GA works and look at a basic sketch of the GA algorithm. So tell me if you can see where I'm writing on the board, otherwise I'll come up with some other solution. Genetic algorithm has a number of features. Basic idea of the genetic algorithm is to start out with a number of potential solutions. So here I've called these solutions, for instance, x1, x2, x3, x4, x5. Now imagine I call them X's because they're points that will correspond to points in our search space some way. We're trying to minimize some, maximize, in this case, the fitness of some function X. So these are our points in the landscape. Unlike, for instance, gradient descent or simulated annealing, you think about gradient descent, you put one point down in your space, and you're going to move towards this point of minimal, or if you're ascending, to ascent. What happens with the GA is conceptually different in the sense that rather than start with one point, we expect there to be many different minima, and we drop down the number of points on this landscape, which we hope to search over. Okay, so how do we move once we have dropped all these points on the landscape which we wish to search? Well, we want to know how good our potential solutions are. So for each of these points, they're going to be at different heights on this landscape which we hope to ascend. So we take the fitness values of all our points. Okay, so perhaps this one has a fitness of 10, maybe this one has a fitness of 20, maybe this one has a fitness of 20, maybe we have another 10, maybe we have another one, say a fitness of 40, where fitness is the name that we're giving this landscape we're trying to ascend. Okay. And the metaphor, the way the genetic algorithm works, it's supposed to look something like the way we imagine a population of individuals look, in the sense that the population, we create a new population, individuals have children which are near one another in the space, the offspring resembles the parents, maybe you have two different parents, maybe this function is fitness 20, this function is fitness 10. These two things if this is our surface, what I haven't drawn is you should imagine that maybe this is at height 10 from the board, this is at height 20, this is from height 20, this is from height 10, this is at height 40. So even though these are both fitness 10, they're in quite different spaces. We'll see how this goes step through step. So the first thing that we do is somehow we imagine that this population is going to reproduce itself. This is step 3. And the basic idea is that things which have higher fitness are going to be more likely to reproduce, which from the point of optimization, if our goal is to optimize the surface, we figure, well, we should search a little bit more around places which are more fit. So some way, different ways of doing it, we'll discuss this, and then we'll select a pair of parents according to fitness. That's the next step. Then, when we take this pair of parents, the hope is that we can somehow mix the information perhaps between two different parents to perhaps find a better solution. Perhaps your mother was very good at math and your father was very good at sports, but they were both poor at the other. Maybe the hope is maybe we'll have a child who's good at math and sports, and that would be higher fit for both of them. So the hope is, this is kind of an odd thing compared to hill climbing or simulated annealing, is this idea that we can hopefully mix information between points in the space to get a better point. There's other motivations for doing crossover, which we'll get to. This isn't going to be true for all sorts of problems. It probably doesn't make a lot of sense to use a genetic algorithm for linear regression and cross over your partial solutions. But in some things, it might make quite a lot of sense. For instance, you're going to be optimizing the traveling salesman problem. And maybe you have part of the path, this tour that you want to generate, or the city's right on one part of the space, and then you have part of the tour right on another part of the space. The hope is through crossover that maybe in some cases you'll be able to combine that information without too much loss. Of course, you might destroy both the things. There's a certain amount of randomization. Likewise, for the individuals, so we're going to combine the information between two different individuals. Likewise, for each individual, we're going to apply mutation to them in some sense. So these X's are going to have some sort of structure. For us, they're going to be bit strings, but they could be vectors in Rn, and we're going to perhaps mutate each location in this vector. And the hope is if you make a small change to the bit string, it's a kind of a small change to your location in space. And so if this fitness function is smooth in some way, somehow you're doing some local search, which makes sense. If you want to improve where you are, you certainly do need to do some form of local search around you. So you do this, you have your 5 individuals. We repeat this process until we get a new generation, and we continue. And then we're going to have some sort of termination condition, which is maybe, well, our algorithm is run for 500 steps, and we don't want to run any longer because it's going to take too long. Or maybe we have to, it's measuring, it seems like the fitness hasn't changed for many, many generations, and so we'll also terminate. This termination condition is something that's going to be controlled by you, as are steps 3A, B, and C. Okay, so that's the broad idea. So for any given problem, we'll consider some representation of the problem. For ease, and in this lecture, we'll do binary representation. For your coursework, and we'll come to, we'll discuss representing permutations, which will be next to the traveling salesman problem. We're going to define some fitness function for your algorithm. The way we've set this up, we're always maximizing fitness. Maybe you have a problem that you want to minimize. So if you need to minimize something, maybe your fitness function is 1 over this problem which you want to minimize, finding the minimum, finding the maximum if you do 1 over, for instance. And then we have to discuss how we're going to select parents based on their fitness. We have to discuss how we're going to mutate and how we're going to cross over, and this is going to depend on our particular problem setup. And we're going to need to tune the algorithm in some way. So we'll come up with the termination conditions, and we'll set this probability of crossover and mutation. Going back for a moment, I want to point out the work here, the work of the user is in choosing this representation and choosing this fitness function. Often for a given problem, you're going to have to experiment. You're going to have to try a slightly different representation. You're going to have to tune it. This is a bit of art and not just a science in some sense. Okay. Okay, so perhaps we imagine that we want to represent our problem. Maybe we want to represent a set of natural numbers. So we can imagine if we're sticking to a binary representation, we could use, for instance, just a standard binary representation of integers. Maybe we want to represent the integers over a different range than, say, 0 to n-1, where n is the number of bits. what if we want to say represented, what if our range of possible integers that this problem takes on is, say, 0 to 9? What's the problem with representing that there with bits?
You have more bits than you.
Yeah, if you say you represent it with 4 bits, that gives you 0 to 15. So how might you solve this problem then?
Just restrict the range.
So what happens if you end up with like 1, 1, 1, 1, 1? What will you do?
Just kill that solution and just generate another one. Flip it.
So this is yes. There's many possible approaches. I think people, there you potentially, for this, you every time, you have almost a 30% chance of getting a bad value, and you have to redo things. So in practice, a lot of people tend to maybe, they use 0 to 16, and then you divide that by the range 0 to 10, and you then round to the nearest thing, or you could use a modulus to solve this also. These are all things to think about a little bit. Maybe you want to have real values, then you'll want to quantize your representation in some way if you're using binary. Something that's very important for a GA typically is, which we'll talk about more later, is how should you organize the parameters. If your problem is controlled by a number of different parameters, does it matter the order in which you put them down in your string? Well, this will depend on your crossover and mutation operators. Okay. So I'd say the most common method of selection, or maybe it's not the most common, but a popular method of selection is called fitness proportional selection, or roulette wheel selection. Here the idea is that, so here we have our sample individuals, F1, F3, F4, F5. What we do is we come up with a discrete distribution such that each individual is selected according to their fitness. So looking at a smaller example, imagine that, okay, the total fitness here is 40, and so this person has 50% of the fitness, so we imagine that we allocate them half of some roulette wheel. This person is 10, this is a quarter of the total fitness, this person is 10, another quarter of the total fitness, and then to select individuals, we simply sampled from the discrete distribution given from those probabilities. So if we have 10 individuals, in expectation, we'd expect to perhaps spin this roulette wheel and create 5 individuals of 1, since this probability would be 50% chance of being selected. Questions so far? Okay, let's continue.
Yes.
Why don't we always choose the most fit? Why do we do this wheel thing?
This is a good point. So imagine for a moment that our problem, we kind of knew we had this surface with a single maximal point, okay? And if we had a single maximal point, we somehow know we always want to search perhaps around, we'd have good reason to perhaps search along the best. We know if we tried to climb that person, that would be the best. But the problem is, suppose you have a landscape with maybe many hills and valleys, and perhaps somebody in your population is the best, okay? But maybe they're only locally the best. So the hope is by doing this with a little bit of randomization that you have a chance to perform well when your optimization function has many hills and valleys. Okay. Other questions? Okay. continuing. Okay, so in our running example, we're going to have a bit string representation. So here for our bit string representation, for our problem, maybe we have this knapsack problem where, we either put an object in the knapsack with a value 1 or 0, we don't put it in the knapsack. So the objects that we store in the knapsack are listed like this, and our goal is to put objects in the knapsack of maximum value, but still meet the constraints of them not weighing more than the knapsack. Very typical hard discrete optimization problem, natural for a bit string representation. How do we generate a new solution nearby to perhaps search something nearby? Well, one operator is mutation, and the idea is maybe I throw a random coin. I have some mutation rate, which I'll say is 0.3. And I throw a random coin, I go, oh, that's not less than 0.3. Oh, that's not less than 0.3. Ah, this is less than 0.3. So these values will maintain the same. This one changed, and so forth. So this is an example of mutating a string. We throw this bias coin, and we see whether we mutate. So now our algorithm has some parameter. In the algorithm parameters, you have to think a little bit, what's a sensible way to choose the parameter? So, well, let's think about what's the differences. So suppose we chose the mutation parameter as extremely small. What would be the problem, potentially? Yes?
We might mean like a local maximum, and not explore.
Yeah, if we made it really small, like we made it 0.00001, we'd probably never flip a bit, and we wouldn't do much exploration. And we have the other problem. Of course, we set it too high. If we set the mutation parameter to 0.5, well, it's just like we're generating a new random bit string every time, and we retain no information at all. So this mutation parameter is kind of controlling how much you're going to jump around with in your search space. There's many reasonable values for this depending on the search type, but certainly if you're setting it to an 0.1 value, for instance, like 0.1 is too small. If you're setting it way smaller than chromosome length, it's probably too small. I meant the other way, too large. Typically people choose it around 1 over the length. So on average, you're flipping 1 bit, so you search locally, but maybe you choose it to 1 over the square root of the chromosome length. These are all reasonable choices which you might consider for your individual problem. Okay. Mutation is kind of a natural thing. It doesn't look so different from doing simulated annealing or some local ascent. You're searching nearby. This is traditionally the fact that you have a number of points in your algorithm as you search, and the fact that you often have some form of crossover is kind of what makes a genetic algorithm a genetic algorithm. The idea of crossover, for instance, in a bit string representation, is the following. We choose some point in our representation. And what we choose some point, well, we roll some die, we see if crossover occurs. We roll some die, and if we're going to go ahead and do it, we choose intersection, and we just flip the genetic material between the fragments of the binary string between the two, and so the offspring resemble the parents. Okay. So Why do this? Yes?
Here, the first one of the two strings represents the mother and the father, and it's changed.
Exactly. This is the idea. So this is perhaps the one parent and the other parent, and not sure which is the male and female here. It's difficult to tell. Big strings. And they. So what I've taken is we've duplicated the information. One parent duplicated the information, the other parent on one side, and then we've interchanged. Okay. Why do this? Well, later on today I'll ask you to maybe come up with another motivation for it, but the classical motivation is this idea of the building block hypothesis from Holland, which is that you imagine that this bit string has, somehow we can have laid out a sequential list of traits, maybe where each trait corresponds to a single bit, and somehow these traits are more closely related to one another than traits which are farther apart. And so the idea is that perhaps one parent, this is really, perhaps, if you're building a car, it's much better for your car to run on gasoline than, say, Coca-Cola, okay? And this is a car that uses gasoline but has square wheels, because this codes for gasoline, this codes for square types of wheels, whereas this car might run on Coca-Cola but have round wheels. And so the hope is that when we, not quite the most realistic example, but when we now maybe have one car that runs on gasoline and has round wheels, and then we have the other, the child who's not going to have much of a future, our Coca-Cola car with square wheels. Okay. This is the idea that somehow that one solution, that there's something discrete about these things, that you can break this up into these parts, and that by grabbing one trait from one thing and another trait from the other, that there's some chance of combining and getting traits in this fashion. So it's a way of somehow hoping to merge parts of solutions. People often, some common variety of crossovers is rather than having that bit string, for instance, listed as a sequence, maybe it's listed circularly, and you grab one area and you put it in the other area, and vice versa. Why is that? Why do things like this as opposed to the other way? Well, this is related to this idea that somehow on your bit string you want traits which are near one another to influence one another. And if somehow the topology of your problem is naturally, this ring form, maybe it makes sense. It's not a bit string, but think for a moment about a traveling salesman tour. A traveling salesman tour, you're building this tour of a graph. There's no start and there's no beginning, because they're all equally the start and the beginning. So it makes sense to have some sort of circular symmetry when you order your traits. Okay. On the other hand, imagine that maybe this bit string represents a series of things that you can invest in, and things are getting perhaps maybe ever more risky, or things can happen at ever later dates, something that has a natural temporal order, and so you expect that there's no symmetry between the start and the finish, that you have some kind of natural linear order, and you've ordered things such that similar things are most similar to one another in this linear order. Questions so far? Let's go on to the next variant. There was a. Did I? Oh, I didn't put it down. Another typical crossover variant is the following. Maybe we have a bit string and there is no ordering, i.e., the trait next to A is not at all related to the trait next to B and so forth. There's no kind of natural ordering. Well, then maybe there's no real sense to grab a string here and grab a string there. People then, in this case, do this uniform crossover, and they just grab bits randomly across between the two bit strings. But usually for a GA to be good, it makes more sense that your crossover is related to some ordering. Okay. Typical GA, which you'll soon have some experience with. It's very hard to get your GA to evolve for too long and be doing something useful in many cases. It's some sort of delicate tuning of the parameters. It depends on the problem and how you set the parameters. But two common things that kind of go wrong with your GA are the following: is one is this idea of premature convergence. In premature convergence, the idea is that maybe you start out in your first generation, and rather having something that looks like this in your first generation, you have instead something that looks like this. You have some individual with 400. So what might happen in this case? What would happen with roll-up wheel selection?
That one will dominate and order to show
Yeah.
you.
We imagine, we throw this up, this is like it's not super dominating, but this is like 450, there's a good chance when you do the selection step, you might only select this person. And maybe there was useful information to be gleaned by searching a little bit more locally in other areas of the space first, and you suddenly start having all copies of this solution dominating the space before you've really generated any coverage of the space at all. Okay? So this is a problem. Another sort of problem is maybe, let's go on the other side. Let's pretend for a moment that your goal is to really find the maximum. And maybe, all these, maybe this is like 399, maybe this is 395, maybe this is 403. We don't know this in advance, but maybe there's some maximum value around 420. And maybe there's reasonable information around this thing. Maybe it's only like a few bit changes that we really need to slowly creep up at this point from around this solution x1. We're not. This is on a local field and it's not so far from the 420. So between these solutions, it's not much difference if the scale is from 400 to 420. But the GA will no longer particularly search around here, and all the things are quite large, so it'll really see no difference between the solutions at this point. Where somehow you can imagine what you want the GA to do is kind of zoom in at this last point and kind of discount away this 400 term and maybe only look at these small relative differences and use that to drive the search, so you have some chance of getting out the last few bits of your objective function. Okay. Just give you a brief overview of problems that people typically think about here. So, this is probably likely to happen for many problems with roll-up wheel selection, but it can also be caused by choosing some poor fitness function. Like you have some problem where somehow all the values get scaled up really large, and no matter what, all the values are really large and they're all near one another, so your roll-up wheel has nothing to work on. You have to think about how you choose your fitness function. If you're using roll-up wheel selection, you can't choose some arbitrary fitness function. You have to hope that you're going to be able to distinguish between different values. So different kinds of solutions have been proposed. People like roll-up wheel because it's natural, it's easy to analyze, because it's kind of simple, but it does tend to have some problems in practice. Even though in your coursework, I believe it works quite well compared to other selection methods, but you may wish to try that. In many genetic algorithm packages which you could use, or you implement them yourself, many varieties of it, but they often implement some form of fitness scaling, or you can turn on a fitness scaling feature. The idea is that we'll still do fitness proportional selection, but now instead we'll rescale the fitness function dynamically in some fashion. Okay? So how should we rescale that fitness function dynamically? So we need to choose some metric doing a linear rescaling. We need to choose some parameters A and B to do this rescaling. So the typical idea would be maybe we want kind of natural we still want to maintain that somehow the average member of the population get one child in the next generation, just like if we use the unscaled fitness values. If you had fitness which was perfectly average, you'd only expect to get one child in the next generation on average. So we still want to maintain this property, but we want to fix the problems of premature convergence and or that lead to premature convergence or stagnation. So what happens in the premature convergence scenario? Here, the best individual, like when we had that 400 thing, on average had, I think, 10 copies in expectation, and then the next thing. And if it's getting more copies than the whole population size, it's going to dominate that population. In this situation, we'd really like to search around 403, but everybody's getting on average one copy. So a typical idea is that you set some parameter C molt to be some value in this range 1.2 to 2. This is just a rule of thumb. So the best individual gets more copies than everybody else, but it doesn't take over the population extremely rapidly. And then you solve for your constants, and more details can be found in that text. Okay. Okay. Present two more methods which are popular. A typical method, another method that we might use is this idea of rank selection. Okay, so in rank selection, we have the following scenario. We have our fitnesses. So here, for instance, F1 is the most fit, F4 is the second most fit, F3 is the third most fit, and F2 is the least fit. And we ignore the fitness values except for the relative rankings. And what we do instead is assign each of them these ranks where the most fit has the highest rank and the least fit has the lowest rank. And then, perhaps you use those ranks directly for some linear fitness function, So in this case, the first, how many children if we use this with the simple linear function where we assign these as the fitness, how many children on average would we expect to generate in the next generation for the first individual? So the idea is now the first individual, we assign its fitness. We reassign its fitness according to its rank. So the first individual has fitness 4, the second highest ranked individual has fitness 3, 2, 1. So how many children in the next generation would this individual have an expectation if we then use roulette wheel expectation on the ranks? Yes?
You're saying that would have 4/10 of the...
We'd have 4/10, and if you have 4 children, it would be something like 4/10 times 4. So in this case, 1.6 children. A little bit. I know some European nations. Okay. So, and the least ranked here, 1 would have. But but there's many potential recommendations that you can try. You can add an offset to the ranks. You can use quadratic scaling, some other polynomial scaling. I used to do labs in JLT and MATLAB. This is for those of you whose only language you're familiar with is MATLAB. You might want to download this package. JLT has some evolutionary computation demos, but I don't know. I don't find it to be the best thing. But if you're only familiar with MATLAB, this is a package that you can use to experiment with GAs, and I find it slightly easier than some of the other more complete MATLAB GA toolboxes. So what do you see as the potential advantages and perhaps disadvantages of using this rank selection?
Doesn't take into account how much better the highest rank is.
Yeah, I guess sometimes we might feel, maybe we somehow we get a little bit nervous throwing away the absolute values, and we're throwing away information when we go to the ranks. This is a trade-off. Often it's much easier to work with your algorithm when you rank things, and many problems it works better, but some problems it doesn't. The throwing the information away hurts you. So that's the disadvantage. And the advantages are it's much easier to cope with. You don't tend to suffer from these issues of premature convergence or stagnation, and the same way with the reasonable scaling. Okay. Another popular method, tournament selection. What's tournament selection? Now you have your population of n individuals, and so typical thing is maybe you say tournament selection with parameter m That means to do selection rather than doing a roulette wheel, you choose 3 people uniformly at random. So I flip 1 through 5 here 5 times, and maybe I choose x3, x5, and x2. Maybe you do it with or without replacement. Then you pretend they have a tournament, and of course I've run into a little problem, but they fight it out in the arena, and the fittest person wins. So in this case, either x3 or x5 would win because they're equally fit. Often tournament selection sometimes has another parameter p, to make it, somehow less aggressive. This parameter p would then say you choose m individuals, and then with probability p you select one of those m individuals at random. With probability 1 minus p, you let them fight it out, and the most fit person survives. So I think we have perhaps probably the same disadvantage of before with tournament selections. You get a little bit nervous. Once more now, it's not the absolute values of the fitness that matter, only the ranks. But now we have, and besides the kind of nice thing for premature convergence and stagnation, I can think of at least 2 nice advantages associated with tournament selection. That rank selection wouldn't have. These are kind of take a little bit of thought to come upon, but maybe you have some ideas, or you can come up with other ones. Yes?
I was going to say, does it cancel out the bad genes quite fast?
So cancel out the bad genes quite fast. I mean,
if you have like a big, say you select like a big group, if there's just one good one, then it will just take away all the other bad ones. So if you have one bad one,
but if you had one good one, it might actually never end up in a tournament.
Oh, okay.
It's no more aggressive, depending on tuning, than rank selection. You can make this by choosing the parameters carefully. You can make it so they have the same expected distributions as linear rank selection with a little bit of thought. I'm not going to go into that detail there, but that would be a little problem one could solve, is how could you set the parameters to tournament selection and rank selection so that each individual in the next generation has the same probability of selection under both of these methods. But it's a mathematical side. I'm looking for different type advantages that can't be explained by the distribution of the children. Okay, let's take a break for 10 minutes. Maybe we can come up with some ideas after break. Otherwise, we'll return to this when break is over. Okay? See you in 10 minutes. If you have any questions, please ask now or then. If you didn't collect a handout or a set of slides, please do so.
Okay, so you just take a log of that. So you just have like you can put outside of the log because you're still referring to the D only. You're still only referring to the N, the I, the D only. So log is like that. So you don't need this information. That's I D.
Let me start.
And then
I'm still waiting for
one.
the person. This is done by two.
So, no, when you get the sensors, they're also
Like
this,
tempting to
plus
aggressive
one this,
genetic stuff.
and then minus. So then
There was one that you gave.
the I F. Okay, so
Yeah,
these are procedures of
no,
get
it might be more like
X I D
by him or.
over the I
I'm not sure. Maybe not.
plus minus 1 over 1 minus 3i. Okay, and then plus X I D over we get this. Plus because it's zero, just consider zero. Well,
I haven't decided.
Convert, yeah,
Just
convert.
because I am taking 5. Because that I want to
Yes. This, what does this represent? Extra chromosomes. Imagine these chromosomes are X values over some landscape. X is the fitness function.
Yeah, that's all of
And these are the values. Yeah, well, the landscape doesn't have any three-dimensional quality. So imagine these values correspond to the.
So I'm going to try the summation X I D
Correct.
equals to, we don't need the summation from, sorry, this was
Yes.
so you only have one summation from PD, but the
So
summation.
suppose you had one value which was much larger than
Like,
all the other
I,
values.
you don't even have like,
During competition, that's what happens in the selection step. We grab individuals.
Supervised learning.
No, within the
If you sum over the eyes there, there's PD
each of those selection steps, it'll end up being population will rapidly gather around that point in space, and you can lose all the diversity of populations. Yes, but it could be that what's happened is you've kind of put all your search on one area of the space and actually this happened on the first generation, for instance. You probably haven't searched around too much and you've lost a lot of variety. Maybe there's other place here which has a value of 8,000, but since everything's now focused here, there's not to look what comes to individual.
Yes, that's the
That's the problem. So if we prematurely converge before we're doing more exploration.
Even like most of the stuff we did using
So you don't
simple
care about data
linear algebra,
that
not
knows
matrices,
some other
not with matrices. So it's quite
That's like
it's not
happening in
hard, but they make
like
it
in
a
lab,
certain
in
case that
experiment,
we need specific for.
everything in the same
Just taking the
environment,
graph
and you just
test
test
subjects.
so
Like
when
most
you
of
say
the
that everything together
it's a mathematical
I
computing.
mean geographically,
They don't allow me to
You can think of an
do
optimization
analysis
problem
and
geographically.
get my
You're trying to, you have a search
Nice.
space, you're trying to find, say, a maximum point in that search space. And so if you end up with 5 individuals, all of the values x1, it's like each of these points,
because there's no point in me taking
all your search effort is concentrated right there. It happens real quickly. And limitation is only going to change things right around there. Crossover, if you cross over two individuals that are exactly the same, they're not going to change. So you're unlikely to move much after that point in time anymore.
There's a lot of work, then I'll have
And
to
so-
make sure I don't leak out the others.
Yeah, we should have prevent, we just should have.
This is the danger of premature computing.
Anyway, it's a
so you cannot
thing
observe
for me
all
that is like,
the other mutations.
already
You won't be observing other points in your search space. And then these x values represent points in space also function for general cases.
No, I have enough for the PhD. In the sense, I keep reacting a different PhD offer, so it still stands after.
You care about optimizing the function. No, you want to find good solutions. So it's not that you don't care about statistics particularly, you want to find a good solution. To the problem. And the problem with premature convergence is that your search method has converged perhaps sooner than you would like it would.
Yeah.
So
you're no longer
That's why I was
exploring space.
that is good showing up.
Feel free to, other people might have the same questions, so if there's a similar question to just ask it again.
Who told you? Google people.
Yeah.
Yeah, I've looked at some iteration says that if you go to this
If you send the email, I can bring to you. Of course, for some of my webpage, I should have an extra copy of the coursework.
You have to take a copy, like they have the
Coursework but I'll use this now.
and
I'll give you my copy. If you want notes from last
quite
week, I
nice to
can
have some
give you them from my office.
ground
Okay.
beats.
Does the book come with the second copy?
So yeah. It seems like the statistical parts are not that mathematical
No.
because just the fourth line.
Yeah.
Because the stuff is more mathematical remote
Statistical applications, then I would have another whole time to catch it up. There's a lot of planning going on right now.